Here is video 1 of chapter 11. Chapter 11 is on intermolecular forces, so it's the interaction between molecules and how that affects their behavior. So first, just quick review of the different states of matter: gases, liquids, solids. The biggest thing I'll re-mention here is that gas molecules are very far apart from each other. Therefore, they don't interact very much, and they're not very attracted to each other or repelled because they have so much space. Whereas liquids and solids, they're very different because their molecules are very close together, and therefore they interact very, very much, and they may be attracted to each other to various degrees. So we talk about these different types of attractive forces. They're going to be broken into two big categories. The first being the primary or bonding forces. These are super, super strong forces. And then you've got the second group, which is intermolecular forces. They're also called van der Waals forces, and they are relatively very weak. Okay, and that's what we're going to focus on more. But first, let's talk about these primary examples. We have ionic bonding as one of them. We're going to have this ionic bonding forces when we have ionic compounds, which means you've got a cation and an anion. What they do is they set up as a lattice like this, especially when they're in a solid form, and you can tell that there's going to be attraction in every direction. This chlorine is going to have 4 sodiums around it, and these are all supercharged, a complete positive and a complete negative charge, and that's going to hold them together very, very strongly. So any example would be a metal and a non-metal. Then you've got what's called metallic bonding. This is when you have just a plain old solid metal, like silver, a bunch of silver atoms, a bunch of iron atoms, a bunch of copper. So just one single metal. And what it does is it also forms kind of a lattice or a web, you could say, of these electrons and protons in a very organized manner. And it holds these metals together very strongly. So metallic bonding applies to plain old metal atoms. And then the third one is covalent bonding, which is covalent network. This is a really specific scenario for covalent bonding. It's when all of the atoms in a solid are directly and covalently bonded to each other. So it's a web of covalent bonds. Like all these carbons, they have 4 covalent bonds in every direction. These are super hard substances like quartz and diamond. This is only going to apply to really 2 elements for us, silicon and carbon. It'll also be silicon dioxide here. But silicon and carbon, they both are able to make 4 covalent bonds around themselves. So they are good candidates for this because they can make that really structured web that makes them very, very hard substances. So substances with these 3 primary forces are super strong solids. They're very hard to break. They also have very, very high melting points because it's really hard to break these molecules apart from each other. Okay, and on a weaker sense though, are these things called intermolecular forces. And we define them as attractive forces between neighboring molecules. So now these molecules are not bonded to each other like these carbons were. It's just that they're neighbors and they have some attraction for each other. So the 3 types that we'll talk about are London dispersion, dipole-dipole, and hydrogen bonding. Let's start with London dispersion. These are the weakest of the intermolecular forces, and they are between all molecules. So every type of molecule will experience London dispersion forces, okay? What these are is interactions due to what's called a temporary dipole. So what I have done here is drawn a bunch of helium atoms, well, 3, I guess, 2 protons and 2 electrons, 2 protons, 2 electrons, 2 protons, 2 electrons. If I think of just a helium atom, I don't think of any polarity, because remember, polarity is if you have a side that's more negative than positive. Well, you would only have polarity if the electrons squish to one side, making that side negative and the other side positive. That could happen temporarily. And what that could do is it could induce a dipole, another polarity, to the neighboring helium. See if this makes any sense. And all I've done here is just draw an attraction. This is not a bond that I've drawn here. But here's another helium atom, right? If these two came in contact with each other, and these two electrons happen to be on this side of the helium atom at this moment, does it make sense that in this first helium, this side of that helium atom would be partially negative? This is a little delta symbol. It's almost like a figure 8 that's incomplete. Delta negative means partially negative. And what that would do is make these electrons on this helium run to the other side, leaving this side partially positive and making this side partially negative. And then when that comes in contact with another helium, it's going to do the same thing. Make these electrons scoot to the other side, causing a positive and a negative. This is all temporary. It's not a polarity that is permanent, but it does cause a temporary interaction and attraction between these two atoms, because the negative side here would be attracted to the positive side here. Once again, it's a very weak force. It's not very strong, okay? And what would happen here is these atoms would be a bit more attracted to one another at this moment. So this is between an instantaneous and an induced dipole. And it's based on this property called polarizability, which is how easily an atom's electron cloud can be distorted. So how easily can the electrons be squished to one side and create a negative or a positive? Well, what we know is that the more electrons are in an atom, the greater its polarizability, because the more electrons you have to work with, the more negative a side can become, and then the bigger the polarity. So here what we say is, if you are comparing polarizability or London dispersion forces, the greater the molar mass of the molecule, you're going to have greater number of electrons, and therefore you have greater polarizability. And lastly, what that means is you have greater London dispersion forces. So if we are comparing molecules, here's kind of the two rules you would look at. I know it gets a little full here. Here, let's focus on E. First of all, London dispersion is going to be the weakest of all intermolecular forces. And the two factors you'll look at, we just mentioned increased molar mass or molecular weight. That's going to be the first thing you look at, really, is if I'm comparing O2 and N2, I'm going to look at their molar masses based on the periodic table. The one with the greater molar mass will have the greater polarizability and therefore the greater London dispersion forces. So O2 molecules would like each other a little bit more than nitrogen molecules would like each other. The other thing you can look at, which is going to be more rare for us, is the shape of the molecule. If you had two molecules who were identical in the number of atoms, so C5H12 here, what you can see is they would add up the same molar mass, but their shapes are very different. The longer a molecule is, the longer and skinnier it is, the more sticky it can be with its neighboring molecule. So this one would have greater London dispersion than this guy, because if you are not linear and you're kind of a glob or an irregular shape, it's hard for you to get in contact with your neighboring molecule because you're just kind of spheres. You're going to kind of just bounce off each other, whereas if you're linear, you can stack by one another and have greater London dispersion. So that's number one. And the second intermolecular forces are called dipole-dipole. These are not between all molecules. Remember, London dispersion is for all molecules. Dipole-dipole is only for molecules that have permanent dipoles, which what that means is permanent polarity. So we already talked in a previous chapter about how to determine if a molecule is polar. So what we can say here is, if you are polar, then you are going to experience dipole-dipole interactions or attraction. So let me show you what I mean by that. Up here, I kind of tried to draw a picture. If you've got HF and HF, so all you're talking about is just neighboring molecules, right? H and F have different electronegativities. So fluorine is pulling on the electrons more than hydrogen. That makes the fluorine side a little bit negative and the hydrogen side a little bit positive. That is a permanent dipole that already exists by himself. If you have a neighboring HF who exists the same way, then what you can tell is that there can be this dot-dot-dot interaction. All I'm meaning by that is this attraction between the opposite charges of these two molecules. You can see it again here with HCl and HCl, because chlorine is more electronegative, so negative, whereas hydrogen's positive. chlorine's negative, hydrogen's positive, and we have dipole-dipole interaction here. This is different than if you just had H2 or here O2, you have no polarity, right? Because the two O's or the two H's are pulling equally on the electrons. So if you're nonpolar, you do not have dipole-dipole. You only have London dispersion. So dipole-dipole are stronger than London dispersion, and they only apply to polar molecules. So here I gave you one more example. CH4 is nonpolar because remember, if all the surrounding atoms are the same, you are nonpolar. So he only has London dispersion. But if you've got CH3F, you of course have London dispersion because you always do. But because all the surrounding atoms are not the same, you have polarity. So you also have dipole-dipole forces. The third and the strongest London intermolecular forces are known as hydrogen bonding. So here, hydrogen bonding is really just dipole-dipole, but it's a really strong type of dipole-dipole. So it occurs for very polar molecules. The way you're going to know if you fit into this category is you're going to have hydrogen that is directly bonded to nitrogen, oxygen, or fluorine. So here, if you have HF, do you have hydrogen bonding? Yes, because H is directly bonded to F. If you have CH3OH, if you drew his shape, he would be carbon with 3 H's around him and then an OH. If you see OH put together in a molecule like this, you can assume that the O is directly attached to the H since they're neighboring. And so therefore I do have hydrogen bonding because the O is attached to the H. Same with water. O is directly attached to H. However, having an H and an F is not enough. Remember, the H has to be directly attached to F, O, or N. So this guy would have dipole-dipole, but not hydrogen bonding. Look back at the top here to my HF versus my HCl. We spoke of them very similarly because they were both polar molecules. So these two guys liked each other in a dipole-dipole interaction. HCl also liked each other because of a dipole-dipole. But HF also has hydrogen bonding because it specifically has H attached to an F. All that's indicating is that it's a much greater polarity, and therefore this attraction is much more strong than just a plain dipole-dipole. So the HF would have greater intermolecular forces because he would have London dispersion, dipole-dipole, and hydrogen bonding. HCl would only have London dispersion and dipole-dipole. So when we're comparing these, we've mentioned this, but here's kind of a summary of the order. We know that these primary forces knock it out of the park because they are so strong. If you have covalent bonds, that would be for carbon. What I mean is covalent network, really. If you have a web of covalent bonds, you have carbon or silicon. If you have metallic bonding, that means you're just a plain metal all by yourself. Ionic means you're going to be a metal and a non-metal. If any of those scenarios are true, then you have the greatest type of attraction between your molecules or atoms. Down here are our intermolecular forces. And these are the weak ones. And we really look at these more when we have just molecular compounds, all non-metals. And remember, hydrogen bonding is the strongest, and that's H directly attached to F, O, or N. Dipole-dipole is next in strength, and it occurs for all polar molecules. And then you've got London dispersion, which is the weakest, but they are attractive forces that are in all molecules.